We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Getting my feet out. Okay, I'm out. Really looks funny out there. See my glove out there, Jim.
Jimmy Boy, get back in.
Okay.
Good morning, Gordo.
Yes, I am.
How does it feel for the United States to be the new record holder?
At last, huh? By cooperating together in these new realms of infinity.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 71 of the Space Rocket History Podcast. And now, Agena versus the Augmented Target Docking Adapter with some EVA equipment on the side. At the beginning of 1966, the Gemini program had met with success in 7 straight missions, 5 with crews aboard. Not all of its goals had been attained, but many had. Now, the Apollo program was nearing its operational stage. The question was, would NASA end the Gemini program to concentrate on Apollo? Previously, Administrator James Webb had used similar reasoning to end Project Mercury earlier than many desired. George Mueller, Associate Administrator for Manned Space Flight, did not know of any move to close down Gemini, but he was concerned that many engineers in Houston might worry that they were nearly out of a job. To calm their fears, in December 1965, he made a case for flying all 12 Gemini missions. Mueller said that even a cursory glance at the program's objectives showed healthy returns for nearly every item. While medical fears had been erased by the outcome of 14 days in space, NASA still needed to perfect techniques for rendezvous and extracurricular activities. Then, too, an experienced cadre of flight crews was essential, not only for flying missions, but for astronaut and flight control training as well. Leroy Day, Mueller's deputy director for Gemini, passed the reassurance on to Gemini program manager Charles Matthews in Houston. With that potential morale threat put to rest, the engineers could focus on such technical problems as making Agena work. You may recall NASA faced the new year of 1966 in an ambiguous position. High achievement had marked 1965, capped by the exciting and important Gemini 7 and 6 mission at the very end of the year. But the key to more sophisticated missions, the Agena, was in serious technical trouble. Agena had to work in order for Gemini to accomplish several still yet to be obtained goals, such as docking, re-rendezvous, rendezvous with 2 separate targets during a single mission, and high-altitude flight goals that would be indispensable to the Apollo program. But many doubted that Agena could be ready in time to meet Gemini's tight launch schedules. The end of 1965 saw Agena's career in manned spaceflight once again called into question, and this time a substitute target had already been approved for development. Although Agena was the most critical problem, it was not the only problem. Extravehicular activity, or EVA, had been canceled in the previous 3 missions, and it was supposed to be ready to enter a more advanced stage with Gemini 8. But unexpected development trouble demanded a last-minute effort to qualify EVA equipment. It was somewhat reminiscent of Gemini 4 when Ed White succeeded in his spacewalk, but this time NASA faced a more difficult EVA task, which was testing the Air Force's Astronaut Maneuvering Unit, AMU, a far more complex personal propulsion system than White had used. The step-by-step progress was skipped during Gemini 5, 6, and 7. The EVA set for Gemini 8 in mid-March had to bridge the gap. Agena's woes were now chronic. The Gemini Agena target vehicle, GATV, was pacing the program by mid-1965, prompting the Gemini Project Office to consider removing the first production model, GATV 5001, from its job as a test vehicle so it could be used with Gemini 8. However, all such plans went up in smoke with the explosion of GATV 5002, the vehicle that was intended to be used with Gemini 6. That mission, covered in episode 65, would start the most demanding piece of engineering detective work in the entire Gemini program. Efforts to cure Agena's ailments spanned more than 4 months, much of it on a 3-shift-a-day, 7-day-a-week schedule. One day after Agena's failure, on October 26, 1965, the Agena Flight Safety Review Board called an emergency meeting. The attendees had learned enough from telemetry data to list the task that had to be done. First, find out why the Agena had failed and what the fixes would entail for design, performance, and schedule. And second, decide if there was any way possible to use GATV 5001 and how long it would take to get it ready for launch. And third, begin cutting red tape that might slow the work. Lawrence A. Smith, Gemini manager for Lockheed, had already sent the taped recorded telemetry signals to the plant in Sunnyvale, California, where W.R. Abbott took charge of the failure search team. The most likely cause of the disaster was a hard start, backfire, or an electrical short. Abbott's group soon narrowed its search to the engine as the most probable source of the trouble. After reporting to General Ben Funk's full Agena Flight Safety Review Board, Hudson took his sub-panel to Sunnyvale, and on November 1st, they agreed with Abbott's analysis that a hard start had been the cause and that it had resulted from fuel being injected into the firing chamber before the oxidizer. The problem was rooted in NASA's original specification for a Gemini target vehicle capable of starting and stopping its main engine 5 times during a mission, in contrast to the standard Agena's 2-start engine. This 150% increase in demand on the engine at once raised the problem of fuel and oxidizer economy. In the 2-start engine, the oxidizer began flowing first, while a pressure switch restricted the fuel flow until a given amount of oxidizer had reached the firing chamber. This was known to enhance the engine's starting characteristics. But it was also wasteful. Oxidizer leaked through before engine firing, and some continued to flow after shutdown. The oxidizer would be gone long before the fuel ran out, so Lockheed accepted a proposal by the engineer subcontractor, Bell Aerosystems Company, to remove the pressure switch and thus allow fuel to enter the chamber first, which turned out to be the wrong way to do things. Abbott concluded that in space, the presence of fuel in the thrust chamber had caused the engine to backfire when the oxidizer reached the chamber, causing an explosion. When General Funk's review board met in Los Angeles on November 3rd to make tentative plans for the engine requalification program, Abbott presented his findings, which were discussed the next day. But Abbott's and Hudson's group were not the only ones working on the problem. At NASA headquarters, Associate Administrator Robert Siemens told George Mueller to form a NASA review board to look into all aspects of the failure, both technical and managerial. Mueller appointed MSC Director Robert Gilruth, co-chairman of a Gemini Agena Target Review Board, and asked Air Force Major General Osmond Ritlin to serve with Gilruth. And down at the Cape, Lockheed's Wolfgang Nogerath was working with MSC engineer Horace Whitaker to pinpoint the cause of the failure. Unsure that the two of them could explore the matter in the depth needed, Whitaker suggested that Lockheed sponsor a symposium of rocket experts from around the nation. The two-day symposium began on November 12th with 19 scientists and engineers in attendance. Nogerath and Whitaker told the visiting experts that the most likely cause of the Agena explosion had been a premature engine shutdown. Engine firing had produced several oscillations and mechanical damage. Temperature decreases had indicated fuel spillage. When electrical circuitry failed, the engine stopped, but a valve that controlled tank pressure as fuel was being used remained open. As fuel stopped flowing, pressure built up in the tanks, which ruptured and destroyed the vehicle. This was a planned flight safety precaution. Whitaker and Nogerath also reported that the engine had not been tested at simulated altitudes higher than 34,000 meters, since no one believed that the environment above that level made any difference for engine firings. Although Abbott's backfire theory accounted for the oscillations that had triggered the explosion, not everyone agreed that a single cause was enough to explain what happened. But the symposium could come up with nothing better, and on November 15th, it recommended that engines should be modified so oxidizer entered the chamber first and should be tested at simulated altitudes closer to where Agena would be working, above 76,000 meters. General Funk now formed a Super Tiger team of 3 senior engineers to review everything that had been found about the explosion and to suggest some answers to the NASA Review Board. The 3 agreed with oxidizer starting and with firing at simulated altitudes above 76,000 meters. General Funk now formed a Super Tiger team of 3 senior engineers to review everything that had been found about the explosion and to suggest some answers to the NASA Review Board. The 3 agreed with oxidizer starting and with firings at simulated altitudes above 76,000 meters. They also wanted Bell Aerosystems to conduct ground ignition tests for data on engine firing characteristics. The Super Tigers presented these recommendations at a meeting in Houston on November 20th. Then to the Gilruth-Ritlin Review Board, which approved them. Lockheed announced the formation of a Project Surefire Engine Development Task Force to carry out the program. But this did not end the analysis of the trouble. Reports and recommendations from other NASA centers continued to come to Gilruth until March 9, 1966, 1 week before the Gemini 8 flight. While Agena sponsors worked to nurse it back to health in time for the Gemini 8 mission, McDonnell engineers had been thinking of other ways to achieve rendezvous and docking. During launch preparation for Gemini 6 and 7 mission, McDonnell's Gemini program technical director John Yardley invited several NASA officials to his motel room in Cocoa Beach, Florida. He outlined a plan for making a poor man's target by bolting a target adapter to the rendezvous and recovery section of a spacecraft and fitting it to the Atlas booster. An enthusiastic Mueller told Matthews to prepare a defense of the concept for Siemens, who would have to approve it. To avoid any hint that a new development program was in the offing, they decided to call it simply an ATDA, which stood for Augmented Target Docking Adapter, which accurately reflected its status as a rearrangement of already developed and qualified hardware. An immediate question was whether the Atlas launch vehicle could handle the proposed ATDA. It was lighter in weight than the Agena, but lacked an engine to boost it to orbit. A call to General Dynamics in San Diego posed the weight question and received a positive response. Atlas could handle the weight. By December 5, 1965, Matthews had the case for the alternative vehicle ready, while Day filled in Siemens' office. Mueller described the plans to the associate administrator himself, who approved it. 4 days later, a statement of work for the ATDA was ready, and McDonnell began building the substitute Gemini target. This target adapter became something of a sword of Damocles over Lockheed, a weapon that the Gemini Project Office was willing to use at more than one level. Jeremy Hancock spurred Lockheed's efforts by sending Smith a picture of the alternative vehicle, often called the Glob, and Matthews asked Flight Crew Operations for an alternative flight plan, eliminating all Agena maneuvers from Gemini 8. Meanwhile, Project Surefire was already running into trouble. The crucial simulated high-altitude test of the Agena's modified engine could only be run at the Air Force Arnold's Engineering Development Center in Tennessee. But it was booked solid. Time was running out for Gemini 8, scheduled for mid-March 1966. John Hudson flew to Vandenberg Air Force Base, where he persuaded General Bernard Shriver, Air Force Systems Commander, to sign a letter moving Agena to the head of the line at the Arnold Test Facility. The Agena test program also got a priority from NASA. When Mueller decided that the Apollo lunar module engine test at the Arnold facility could be postponed. By December 17th, after Bell had completed the Project Surefire modifications, the Air Force accepted the main engine for GA-TV 5003. Bell had already begun the series of 48 sea-level firings that the Super Tiger team had recommended. And on January 18th, the Gemini Agena target vehicle 5003 arrived at the Cape, which meant that Agena still had a chance to compete with the ATDA for Gemini 8. February 14th became the deadline for making the choice, while Gemini Project Office kept working on both the ATDA and the Agena. Late in January, Gemini Project Office engineers went to St. Louis to conduct a design review of the ATDA, and Gemini Procurement received word to put through the final papers for its purchase. ATDA development was quick because its parts had already qualified for spaceflight, and good luck held its costs down. A spacecraft rendezvous and recovery system fished from the sea for post-flight examination after the Gemini 6A mission could be used in building the ATDA. McDonnell put it together by February 1st, and NASA conducted the acceptance review the next day. The stand-in for Agena was ready to assume the starring role. Agena was clearly trailing its rival, but its sponsors hoped to regain lost ground when the second act of the test program began at the Arnold facility on February 7th. Meanwhile, Hoffman and Smith had sent their written reports on static firing to Mueller. In Hoffman's view, static firing was mainly useful for training launch crews, not for proving rockets. He pointed out that Mercury Atlas I had failed at launch, even though it had been static fired, and that static firing would not have disclosed GATV 5002's problems. Smith stressed the penalties in money and time. A quick poll of opinion from NASA headquarters and the Manned Spaceflight Center supported the Hoffman-Smith viewpoint, and Mueller dropped the notion of static firing the Agena. That was a plus for Agena's prospects, but the test program at Arnold produced less happy results. After the first 6 tests, problems with mismatched hardware had already compelled the Gemini Project Office to direct McDonnell to speed up its ATDA testing. The 7th test on February 12, 1966 was nearly fatal. Fuel lines contaminated by alcohol and water caused a hard start that badly damaged the engine. Fortunately, Bell had just about finished its series of sea-level tests and could send that engine to replace the damaged one. As Agena's time seemed to be running out, its proponents literally worked around the clock, juggling, cajoling, scheming, begging, and snarling when necessary to reach what had begun to seem an impossible goal. More than once, Day and Matthews pleaded with Mueller to keep the Agena. Finally, he gave them 1 week to return the vehicle to good health in time for the review board meetings to be held in Washington on March 6th and 7th. On March 1st, the new test series began at Arnold, and by the end of the 4th day, 22 firings at simulated altitudes of 83,800 to 114,300 meters had proved the success of the modifications. Meeting as planned, the Design Certification and Air Force Flight Safety Review Boards approved the modified Agena for flight. The Agena had been requalified just in time to fly on Gemini 8, and the Agena rival, ATDA, was also ready, having completed its test program on March 4th. Now, the ATDA went into storage at Cape Kennedy to be called out if Agena failed again. While one group in the manned spaceflight program struggled to restore the Agena, another faced qualification problems on a smaller scale with extravehicular flight equipment. Ed White's spectacular spacewalk during Gemini 4 was backed by a comparatively simple technology. That first step into space had merely required an astronaut to leave the cabin and see what he could do. White did it in grand style, making his flight plan as he went along. His successor would not be so free, as he attempted such specific tasks as retrieving experiment packages. The ease of Ed White's spacewalk misled mission planners into thinking that EVA would present few, if any, problems. No one really worried when spacewalks were deleted from the missions of Geminis 5 through 7, even though the Complex Astronaut Maneuvering Unit, or AMU, was still scheduled for Gemini 9. The AMU was designed by the U.S. Air Force, which was planning to use the Gemini spacecraft as part of a manned orbiting laboratory. The AMU was designed to make an extravehicular astronaut independent of spacecraft systems. It was a box-like backpack with sidearm controllers and supporting shelves where the hydrogen peroxide propulsion system and the life support oxygen supply were mounted. Since the Gemini spacecraft was so small, the AMU was housed back in the adapter section. The astronaut would go out the hatch, tied to a tether, make his way to the rear of the spacecraft, and strap himself into the AMU. This special propulsion system weighed about 76 kilograms, which was no burden at all in weightlessness of space. The EVA equipment planned for Gemini 8 was intended to be a proving ground for equipment and procedures before actually using the AMU. 3 weeks before the crew was announced, McDonnell held a briefing on the extravehicular gear Gemini 8 would carry. It comprised 2 main units, an extravehicular life support system called the ELSS by the engineers who worked on it, and an extravehicular support package known as the ESP, or more commonly, the backpack. The life support system was a chest pack designed to do just that, feed vital oxygen to the spaceborne astronaut from the spacecraft's supply, from a primary source in the backpack, and from its own emergency supply. The backpack did more. It was designed like the AMU to fit into the spacecraft's adapter section. It carried, aside from its own oxygen supply, a radio and 8 kilograms of propellant for a zip gun maneuvering unit. The backpack was connected to the spacecraft systems by an 8-meter oxygen hose tether. Once the astronaut had switched over from the spacecraft to the backpack oxygen supply, he could add a lightweight 23-meter tether to the shorter hose and, theoretically at least, maneuver as far as 30 meters from the spacecraft. The question to be answered now was, could the extravehicular life support system and the extravehicular support package bridge the gap between Ed White's tethered spacewalk with the zip gun and the Air Force's AMU? NASA hoped to answer that question on the flight of Gemini 8. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.